morning again. And I will talk about graphs and Skeleta of Polytopes. So essentially, this is my talk will be about the combinatorial theory of convex polytopes. So let me start by reminding you some basic definitions. I should apologize in advance for the experts in the audience that the talks is meant to be quite boring for them. And if they're not bored, they should tell me, and it means that I'm not doing my job properly. So a polytope, or a d-dimensional d-polytope, which is short for d-dimensional polytope, is the convex hull of a finite set of points. In RD. And let's say finite set of points in RD which finally span RD, otherwise it's a lower dimensional polytope. So this is a polytope, and polytopes have a nice phase structure, which is our main interest. So a proper phase of a polytope is the intersection of P with a supporting hyperplane. So this is a proper phase, and we also add the empty set and the whole polytope as trivial phases. And we would like to understand the set of phases of polytopes. So, the combinatorial theory of convex polytope is understanding the phase structure of polytopes. I should make two remarks. So one remark about the word polytope here, and one remark about the phase structure. Actually, the combinatorial theory of convex polytopes developed to various combinatorial structures which are more general than polytopes, and I will mention them shortly. So, so this is now important part of this theory. As for phase structure, so there are few cases where we are interested in more refined things about polytopes. Like, for example, when we have a polytope and we have some linear functional, then this linear functional describes some additional structure. It describes a structure on the. It describes an orientation of the graph of the polytope that I will define in a minute. And this is also part of this theory. Also, sometimes we are interested not only in the polytope but also in subpolytopes. Subpolytopes, convex hull of subsets of the vertices, their structure is not derived from the combinatorial structure of the original polytope. So this is another thing we can be interested, or we can consider the hyperplane arrangement described by the faces, by the facets of the polytope. And again, this gives a richer combinatorial structure than just the phase structure. On the other hand, so this is still in the area, the combinatorial theory of convex polytopes. Of course, as you know, there is a very highly developed series of metrical theory of polytopes. Also, there is much interest in integral properties of polytopes, the integer points inside polytopes, which are separate, although related theories. So we have polytopes, we have faces. What can we say? Before we say something about the faces, we'll give some special names to some of the faces. The extreme points of the polytope of P, which are the zero-dimensional faces, zero faces, are called vertices. Vertices. The one-dimensional faces, so one face is a brief for one-dimensional faces, are called edges. And the maximal non-trivial faces, the d-1 dimensional faces, are called facets. Now, when we consider the vertices and the... Now, faces of polytopes are also polytopes. Let me write that. Faces of polytopes are themselves polytopes. And so the one-dimensional faces are one-dimensional polytopes, which are just line segments. And when we consider the vertices and the edges of the polytope, so this is a structure which consists of points and then line segments which connect some pairs of these points, then we can consider abstractly, we can consider this structure as an abstract graph. And this is called the graph of the polytope. So the graph of the polytope consists of the vertices of the polytope, the zero-dimensional faces, and pairs of vertices which form one-dimensional faces are the edges of the graph. So we denote it by G of P. G of P is the graph of P. So you should interrupt me immediately if you have any questions or something is not clear, or even if something is wrong. Okay. So just a few more things. So what can be said about the set of faces of a polytope? Maybe what can you say about the set of faces of the polytope? What kind of object is this? Finite, yeah. So yeah, I mean, everything was said was correct. The first thing, it's a finite. So the set of faces, think of P. It's a finite. It's a partially ordered set. It's a poset. So poset is partially ordered set. It's graded. So every face have some grade in the poset which measure the longest chains leading to this set. So it's graded by dimension, and it's also a lattice. So a lattice means that a partially ordered set is called a lattice if for every two elements there is a maximal element which is smaller than the two and the minimal element which is larger than the two. So it has the lattice property, and this is very important. Some other properties that this thing has? So it's also atomic. So finite, graded. It's a lattice. It's atomic. This means that the elements which are join irreducible, which are not the join of two other elements, are atoms, are ranked in the bottom. So every face which is of dimension bigger than 0 has vertices, and it's the join of its vertices. So it's atomic. And also every lattice, so every interval, so the set of faces of a polytope, let's call it L of P. So this is the face lattice of P. Every interval in L of P, is also a face lattice of a polytope. Okay, so this is perhaps the elementary and basic properties, and let me introduce one more notation. Let's write fk of p is the number of k faces of p. And the vector f minus 1, f0, f1, up to fd of p, this is called the f vector of p. Okay, so we have this basic property, and we can consider perhaps the largest combinatorial class that a large combinatorial class that's very interested in our context is indeed the ranked, the graded, I say residually atomic finite lattices. So this is a combinatorial objects which sometimes, I think some people call them, they are known by different names, I think also by the name abstract polytopes. And these are combinatorial objects which are much larger than face lattices of polytopes, and still some basic properties are so this is this object, and some combinatorial properties hold in this generality. And when I say residually atomic, I mean that every interval is atomic. So every interval is atomic. Okay. Now, so although we study this object, I should mention that there are some creatures which do not lie here and also related to the theory of convex polytopes. Perhaps I'll mention especially there is the Bruja orders and some of the generalization which are related in mysterious ways to the study of convex polytopes, but they are not lattices. Okay, now there is one very important property, additional property of polytopes, which perhaps goes after the first result in the combinatorial theory of polytopes that was not mentioned here. So maybe you know. This is Euler, yeah, this is Euler's theorem. So face lattices of polytopes are actually Eulerian lattices. Eulerian lattices. So Eulerian lattices are lattices where every interval has the same Euler characteristic, the alternating sum of elements in the grades, the same Euler characteristic as a sphere of the same rank. Okay, so the alternating sum of faces of a d-dimensional polytopes is invariant. It's always the same. And if we just adopt this additional requirement, then this gives us already quite a substantial restriction. For example, the intervals of length 2 will all look like this. So they will all look like diamonds. And then the interval of length 3, which correspond to three-dimensional polytope, will satisfy Euler relation. The number of vertices minus the number of edges plus the number of faces is 2. And the intervals of length 4 will satisfy the higher order Euler relation and so on. So this is the Eulerian lattices. This is still very far from polytopes. Polytopes topologically, they are more restricted than just what's derived by the Euler. Yes?
What's an interval?
Yeah, sorry. Interval in a poset. Every time. Yeah, I think. Interval is, so the interval between u and v is the set of all x, so that x is greater or equal to u, less or equal to v. So the interval in a partially ordered set is all the elements which are in between this. Okay, so actually they're not only Eulerian lattices, but they represent, if we ignore the maximal face, then we get something which topologically is like a sphere. So here inside the Eulerian lattice, there are the regular CW sphere. spheres. And here inside there are polyhedral spheres. And inside that there are the polytopes. The polyhedral spheres are regular spheres. So I will not I will not define all these notions, but polyhedral spheres are objects which the cells look like polytopes, but the entire structure is not a polytope. It's just some polyhedration of a sphere. So this is more or less a picture of some of the more general objects we are interested. Let me mention a few of the more restricted objects which we are interested in. And this is a special class of polytopes. I'll mention the simplicial polytopes. So simplicial polytopes, all proper faces are simplices. And the simple polytopes, so this is the dual class, and here every simple D polytopes, every vertex belong to D edges. So this is not precisely the dual description. The dual description is a polytope is simple if when we cut it near a vertex, then we get one lower dimensional polytope. This lower dimensional polytope is a simplex. So for example, the cube, the three-dimensional cube, it is a simple polytope. And the octahedron, which is dual to the cube, is a simplicial polytope. The cube is not simplicial. The two-dimensional faces of the cube are not simplicial. Okay, so this is more or less the introduction. And now let me mention what are the roots of problems in the combinatorial study of polytopes. So perhaps one of the basic root is, as already mentioned, Euler relation. So for three-dimensional polytope, it says the number of vertices minus the number of edges plus the number of faces is always equal to 2. So Euler's relation is the source of a lot of activity in polytope theory, the study of phase numbers and slightly more general invariants in higher dimensional polytopes. And this is a very rich and structured theory that I will not mention. So essentially what I will talk about is the part of the combinatorial theory of convex polytope, which is not F-vector theory. But I'll mention that on the one hand, this is a very developed theory. So there are a lot of results and conjectures, but on the other hand, there are an embarrassing open problems. And since I want to mention quite a few problems, I will just mention one embarrassing open problem, which is problem. It's due to Barani. So it's good that some people who don't work in some field ask you some questions, and then you see you cannot answer them. And this is the following. If P is a D polytope, is it true? Is it true? Or it's certainly true, but prove that Fi is greater or equal to the minimum of F0 and Fd minus 1. So the number of I-dimensional faces is at least the minimum of the number of vertices and the number of facets. So it's very embarrassing that we cannot answer this problem. I should say that this problem lies, if you believe some very far-reaching conjectures, then maybe you can derive stronger results. On the other hand, this should be true perhaps even for all this class, for every graded residually atomic finite lattices. So maybe it's true in this generality. I don't know why. Maybe it's maybe true that up to half the dimension Fi is bigger than F0, and above half the dimension Fi is bigger than Fd, bigger or equal to Fd minus 1. On the other hand, we cannot even show that Fi is greater or equal to the minimum of F0 and Fd minus 1 divided by 1,000 or by any constant. So this is an embarrassing problem, and this is the place where I will leave F vector theory. So let's mention a few other roots of problems. Okay. So the next important source of problems is linear programming. So combinatorial problem about polytopes which arise naturally from the theory of linear programming. So I'll mention a few of them later. So another source of problems is trying to generalize from D equals 3. Three-dimensional polytopes are fairly well understood. For example, the graphs of three-dimensional polytopes are precisely three connected planar graphs. And there is a lot of interest and study of planar graphs. So one source of problems for high-dimensional polytopes is try to extend facts, problems from the case of for planar graph to understand what they say in higher dimension. And then it turns out that there are a lot of relations with combinatorics, geometry, so metric problems, and recently algebraic geometry and commutative algebra, which also introduce a lot of interesting problems, and also no sheer imaginations. In general, the theory or the combinatorial theory of convex polytopes, beside the F vector theory, looks quite sparse in terms of the questions and certainly in terms of the answers that we know. Okay, so I will discuss in these two lectures several sub-areas or sub-properties. So the first thing which I will discuss is connectivity. So this will be the first topic. The second topic will be missing faces and skeletons of polytopes with few vertices. The third topic will be reconstruction. Fourth topic will be diameter of graphs of polytopes. And if there will be time remaining, I will talk also about how small dimensional faces of larger dimensional polytope look like. So small, low dimensional faces of high dimensional polytope. Okay, so let me start with connectivity. And I would like to start. So perhaps very basic result. I ran out of white chalks. Oh, here. No, this is a point. Okay. So let me start with connectivity. So perhaps the first theorem of Balinsky. Graphs of the polytopes are deconnected. Yeah, this reminds me. Once I talked in some. There was special classes for Air Force cadets, and so there were sort of soldiers, and there was a guy who was responsible. So I started the lecture with a chalk that went smaller and smaller. Then I observed that the chalk remained convex all the time, but it became smaller and smaller. I became more and more nervous. And when it reached really a tiny size, then this guy suddenly came up and gave me another chalk. So it's a very efficient way to. So how do you prove? Where are we? I wrote it. What? Under. So what? What happened? This is too complicated geometry. Okay, graphs of the polytopes are deconnected. So. I see. Okay. Graphs of the. So, first of all, what does it mean? It means if you look at a graph of a d-dimensional polytope, this graph is connected, and it will remain connected even if you delete d-1 vertices or less. So, what is the proof? Yeah, so let's try to recall how we prove this thing. So we have two vertices, V and W, and we have here this d-1, let's call them U1, U2, up to ud-1 other vertices. And now, if these are all the vertices of the polytope, if the polytope has only d+1 vertices in dimension d, then this polytope is a simplex. The graph of the simplex is the complete graph, and this is certainly deconnected. Okay, so there is one additional vertex. Let's call it, I don't know, Z. Okay, and now let's pass a hyperplane through the vertices U1, U2, up to ud-1 and Z. So this is the hyperplane H. And we can think about two possibilities. So this is the polytope somehow, and this is the hyperplane. And it is possible that these two U and W are in the same size of the hyperplane. Now, perhaps one basic fact that you may recall is that if we start from a vertex, if we consider, so every hyperplane defines some linear objective function, some functional where this hyperplane is 0. So this is the direction perpendicular to the hyperplane. When we have a polytope, we start from a vertex. We can always, unless this vertex, unless the maximum of this functional is attained at this vertex, then we can find a direction, an edge, where we can improve the value of the linear objective function. This is the basic principle of the simplex algorithm. We start from a vertex, we have a linear objective function, we improve and improve, and eventually we reach the top. So we reach a local maximum, but the basic fact which follows from convexity is that local maximum is a global maximum. We will come back to this point. In any case, this means that here we can go up and reach a vertex where this functional attains the maximum, and also here. Now, the set of vertices where this functional attains the maximum is a lower dimensional polytope, and the graph of this lower dimensional polytope is connected. you know, if you wish, by induction. So we can connect it like this. So this is if they are on the same size. But if they are not in the same size, things are not much worse, because so we have this. So here is U, and here is W, and here is the point Z, which is on the hyperplane. And then we know, okay, so this is the polytope. And then we know that we can go from Z and improve the value of the objective function until we reach the top. Well, U need not be here. It can be here until we reach these top faces. And we can do it also from U. So we connect Z to U. And we can also connect Z to W, Z to V, sorry. And these two passes will, so the pass from Z to U will use only vertices which are above the hyperplane. The pass from Z to V will use only vertices which are below the hyperplane. And we didn't use any of the vertices U1 up to UD-1. So this is a proof of Belinsky's theorem. I cannot guarantee that this is the easiest way to look at it, but Belinsky's theorem is now, it's easy enough by what we know now that if you try to prove it, you will find out a proof. And indeed, the Belinsky theorem, although this proof is very geometric, it extends in much larger combinatorial contexts. Although I'm not, and Barnett had several results on that, although I was not sure when I prepared the lecture precisely how general this theorem extends to, but it's very general fact. So now let me mention immediately some problems, some open problems. And the problem, so this is I forgot one problem. So let me divert a little bit. I mentioned several roots of problems, and I want to mention one problem which doesn't fall into any of these classes. So this is a diversion. This is problem 2. How many graphs of simple polytopes are there, simple D polytopes are there with n vertices. So simple or general polytopes are there with n vertices. So this is quite a basic problem. So in many cases, enumeration or asymptotic enumeration really relate to deep structural properties. And this is a very basic problem that we don't know the answer. For D equals 3, the answers are quite well understood. There is a lot of knowledge about enumeration of planar graphs of various types. And the number is exponential. The big question is it exponential? Is it exponential? I should say only exponential. So for example, when you talk about simple polytopes of dimension D, then the graph is a D-regular graph. So you have D-regular graph with n vertices. The number of D-regular graphs with n vertices when D is bigger than 2 is super exponential. It behaves like n to the n. But there are reasons to believe that maybe the number of polytopes is only exponential. This would be a very serious restriction. And this is for simple polytopes, but maybe it's applied for general. I didn't think so much about general polytopes, so maybe I put general in questions. But maybe it's also. OK. Yes?
I mean, if you have a D-regular graph, then the number of edges is kind of linear.
Yeah, but the question is the number of graphs, not the number of edges.
Right, so the number of graphs on a linear right.
The number of D-regular graphs is roughly n to the D over 2n or something. So even if you here I talk about isomorphism types. Actually, these questions arise in various connections. So it came from different directions. Okay, now let's go back to connectivity. And since we have such a simple proof about deconnectivity, let's mention another open problem. Annoying open. No, I don't know if it's annoying actually, but open problem. So this is a conjecture due to Luckeberg or Luckberg. It says the following. Before, let me make a definition. KL pass between U and V. So this is two vertices of a polytope, is a pass F1, F2 up to Ft, is a pass of faces of K faces, F1, F2 up to Ft, such that the dimension of Fi intersection Fi plus 1 is L, and V belong to F1 and U belong to Ft. So this is the pass, and T is the length of the pass. So pass in graphs is a special case of 2-1 passes of edges and vertices. This is a more general object. So Luckeberg asked the following question. Suppose that D is equal to D1 plus D2 plus dr. It's any partition of the number D, and V and U are vertices, and there are disjoint. I will explain what I mean by disjoint. Passes such that the J's pass between U and V, such that the J's pass is of type dj minus 1. So you have U and V. Say D is equal to 5, and 5 is equal to 3 plus 2. So you have, from U to V, you have two disjoint passes. One is of type 3, 2, so it looks like this. So this is a pass of triangles, that the intersection of two adjacent triangles is an edge, and another one looks like this. And when we say that they are disjoint, we mean there is no common vertices except U and V to any of these faces in the pass. Yes?
In your picture, the polytope is simplicial, but that was not assumed.
Yeah. So let me change the picture. Yeah, I don't know. This is a minimal change just to.
Am I misunderstanding that you might be off by 1? I mean, you want a path of tetrahedra for 3 now. So when you say
Yeah, maybe I'm wrong.
3 is a path of tetrahedra,
sorry.
2 is a path of triangle.
Yeah, so I'm sorry. So yeah. So this is always confusing, how to rank and grade the polytope. And I was wrong. So a usual pass is of type 1, 0, and not 2, 1. And this is, let's say that D is equal to 3, and 5 is 2 plus 1. So this is the pass. Okay, this is the easier way. But I hope you get the picture. Now, when we are talking about a pass in the usual sense, then this follows from deconnectivity. But it doesn't. It follows from deconnectivity, from the definition of deconnectivity by a deep theorem in graph theory, which is Menger's theorem, which says that if a graph is deconnected, then between any two vertices there are disjoint passes, vertex disjoint passes. This is a deep theorem, so we need some substitute to prove it, or some other way. And also for polytopes, I don't know how to prove directly that there are disjoint passes without using Menger's theorem. But this is a nice problem. Okay, now let's talk more about connectivity and refinement of connectivity. So yes. any D1 to DR. Let me mention a theorem. This theorem of Whiteley, and for D equals 3, it's of Alexandrov. It says the following. Graphs of D polytopes with two faces triangulated are rigid. Graphs of D polytopes in RD, I don't know, are rigid. Let me add something, hence generically rigid. So let me explain the words which appear in this theorem. Rigidity is, in this sense, is talking about graphs which are embedded already in some Euclidean space. So the vertices are embedded in RD. The edges are the line segment between the vertices, and rigidity refers to a situation where the edges are rigid. They are built from some steel or some maybe not some rigid material, but they can bend in the vertices, in the vertices. So when we have such a structure, I should say this is for D greater or equal to 3. It's not true for D equal to. When we have such a structure, we call it rigid if the only motions of the structure which keep these edges, the length of the edges fixed, the only thing we can do is a rigid motion of the entire space. So this is the definition of rigid. So for example, when D equal 2, a triangle is rigid, but a quadrangle is not rigid. Well, I don't know. Maybe it is true for D equal 2 with this, because we have to triangulate the whole face. So I don't know. But now, when we are talking about higher dimension, so any simplicial 3 polytope is rigid. There's no way. This is a deep theorem, and this is theorem of Alex. So well, let me say here, infinitesimally rigid. Actually, this is what he. Infinitesimally rigid means that there is no first order. There's no perturbation that fix the length of the edges, at least to the first order. In any case, Whiteley proved and Alexander proved for D equals 3, and this is all based on the famous theorem of Cauchy that 3-dimensional polytope are rigid. If you have 3-dimensional polytope and you perturb them or even you move them such that the 2-dimensional faces are kept rigid, then the whole structure is just the only thing you can do is a rigid motion. And now this theorem as it is not a theorem in the combinatorial, strictly speaking, is not a theorem in the combinatorial theory of convex polytopes because the conclusion is geometric. But the fact that with this embedding the graph is rigid implies that generically when we embed the graph, the vertices, then the resulting graph is rigid. So it's generically rigid. And generically rigid is a combinatorial property. Algebraic property if you wish, but it's a property just of the graph. It does not depend. And this property, so it's not immediate to see, although it can be seen, that Whiteley's theorem, the generic rigidity of graphs of polytopes is a much strengthening of Balinsky's theorem. So as an exercise, I let you to prove the D connectivity from the D rigidity. I should mention that here the D rigidity of graphs of polytopes have further consequences. For example, it has quite a deep consequence for the face numbers. what's called the lower bound theorem and some extension of the lower bound theorem for polytopes. So this already has a lot of information. So just another thing about connectivity, what is the analog of the fact that the graphs are connected for higher dimensional skeleta, for the higher dimensional faces of the polytope? Well, there are notions of connectivity for polyhedral complexes, which are topological notion of connectivity, like being simply connected, that the homology group vanishes, and so on. And indeed, if you take a d-dimensional polytope, then its homology groups vanish. All its homology group vanish. Yes, if you take the whole polytope, including the solid body itself, then this is a contractible object. Then all the homology vanishes, and this is a connectivity property of the fairly mild connectivity property of the higher dimensional skeletons. You can ask for stronger connectivity problems, either of the form of Balinsky's theorem or of the form of Whiteley's theorem. I can let you play with it yourself. What should be the analog of Balinsky's theorem, for example, for the simple connectedness of Skeleta of Polytopes, or of the vanishing of the higher dimension homology. So this is something which is interesting. I should say that all these facts about polytopes, that the homology is zero, has a very strong combinatorial form in terms of what's called shellability. So I will not define or mention it, but there is a very sharp combinatorial statement about polytopes which implies these connectivity properties in a very sharp combinatorial way. And this is something which is true for polytopes but does not extend too much beyond polytopes. I should say that this theorem is not even known. So the generic rigidity of graphs of polytopes, it's not even known that this extends when you triangulate the two-dimensional faces. This is not known for polyhedral spheres, for example. So this is something where the proof works just for polytopes, and we don't know how to extend it. Okay, so this was a brief look at connectivity. And now I want to talk about another topic, and this is the topic of missing faces and polytopes with few vertices. So what do we mean by polytopes with few vertices? Well, the fewest vertices a polytope can have in dimension d is d plus 1. This is the simplex. And the study of polytopes with few vertices is the study of polytopes where the number of vertices exceeds by a constant the dimension, like d plus 10 vertices, d plus 50 vertices, and so on. And already for polytopes with d plus 3 vertices, there are quite a huge amount of combinatorial type of polytopes. And if we're talking about d plus 4 vertices, I think it's quite hopeless to characterize all the polytopes that there are. But still, there is a very nice theorem that I would like to prove to you. And this will be the last thing we'll do, I think, today. And this is the following theorem by Perles. So this is a theorem. It says the following. So let f r d beta be the number of combinatorial types of r-dimensional skeletons of d polytopes with d plus beta vertices. Then, so for example, if r is equal to 1, this is the number of graphs. For example, you can ask, what is the number of graphs of d polytopes with d plus 7 vertices? Or what is the number of two-dimensional complexes which can occur from d polytopes with d plus 1,000 vertices? Then, for R and beta fixed, F R d beta is bounded. So the theorem says that this number, if you fix the dimension of the skeleton and you fix the extra number of vertices, then as the dimension grows, this number stabilizes. You don't get more and more and more types. Okay. So actually, there is a if we are talking about all polytopes, then there is a construction which increase by 1 the dimension and leave the and fix a beta, and this is the construction of taking a pyramid. Yes, so if you take a pyramid, you have a polytope. This is the polytope in some dimension d. This is p. You add another vertex in a different in one higher dimension. Then this is a new polytope, the pyramid over p, and this construction add one vertex, and the dimension go up by 1. And what this theorem says that you can always do this, but starting from some dimension, this is the only thing you can do. Okay, so now let me try to prove you this theorem. So, or explain why this theorem is true. So, I will consider only simplicial. So, for simplicity, we consider simplicial polytopes. But I will tell you later what is the change needed for general polytopes. So for simplicity, we consider simplicial polytopes. And now I will define what is a missing face. A missing face, F, is a set of vertices such that F is not a face. So the convex hull of this, usually we identify a face and the set of vertices of the face. So this set of vertices is not a face, but every proper subset and every proper subset is a face. So missing faces are important in various studies, in various issues concerning convex polytopes. For example, let's see what are the missing. Take this double pyramid with a triangular basis. What are the missing faces of this polytope? So we have so we have two missing faces. One is this triangle in the middle. This triangle is not a face of the polytope, but every subset, its 3 edges form a face. And also this edge, these 2 vertices from the top to the bottom also form a missing face. So here we have one missing face of dimension 1 and one missing face of dimension 2. Or what about the cube? What are the missing faces of the cube? Well, for the cube, all the non-edges are missing faces. Yeah, actually, the cube is not simplicial, so we should be careful about the definition. Let's talk about the octahedron. What are the missing faces of the octahedron? So we have 3 pairs of edges between the antipodal vertices. Okay. So the theorem, so now what we want to show is that the number, so I don't know, theorem, the number of missing faces of dimension less or equal R in a simplicial D polytope with D plus beta vertices is bounded by a function psi r beta. So the number of missing faces is bounded by a function which does not depend on the dimension. Okay, so why this theorem will imply that theorem? So this theorem will tell us that if we have in very high dimension, all the missing faces will be in some small number of the vertices, and there will be a lot of vertices which will not belong to any missing faces. This implies that if we look at the skeleta, then the effect of adding these vertices is precisely, if we look at the r-dimensional skeletons, the effect of adding these vertices, which do not belong to any missing face, is just the same as the effect of forming a pyramid. This does not mean that this polytope is a pyramid. It just means that when we look at the r-dimensional skeleton, it looks like a pyramid. So adding each one of these vertices, if there's no missing faces which involve these faces, this means that every time we have, so this means that we can determine precisely what are the faces which contain any of these other vertices. So the skeleton will look like a skeleton of a pyramid with respect to any vertex which does not belong to any missing to no missing faces. Okay, so this is perhaps this is too short, but because of the time is evaporating, how to derive this theorem from that theorem. Now, how do we prove this theorem? So we need one lemma which says lemma D polytope with D plus beta vertices has at most beta minus 1 disjoint missing faces. Okay, so this is an easy lemma. So I will the proof exercise. Okay, so we cannot have, if we have D plus beta vertices, if we have D plus 7 vertices, we cannot have many disjoint missing faces. Every time we have a disjoint missing face, it's add another extra vertex. Okay, so but I can tell you, try to prove it as an exercise. I can tell you next time how this proved. Okay, now how do we get from this lemma this theorem? So there is a very simple combinatorial way to do it. Well, this is not the original proof of Perles, but this is a variant. He used a different combinatorial path toward it. And this is by the Erdős-Rado sunflower theorem. So the Erdős-Rado sunflower theorem is quite a basic combinatorial result. It's also a very easy result to prove by induction. It says that if we have a large enough so large enough will be greater or equal to some, I don't know, theta of R and beta collection of sets of size R, of size less or equal to smaller than R, then we have a sunflower, then we must have a sunflower of size beta. What is a sunflower? This will be the last thing I will tell you. What is a sunflower? A sunflower is a collection of sets which look somewhat like a sunflower. So here is a sunflower of 3 sets of size 3. So a sunflower is a collection of sets A1 up to AR, or A1 up to A beta, sorry, so that all the pairwise intersection are the same as then. You cannot have too many missing faces, and therefore the number of combinatorial types of skeletons is bounded. If we take skeletons of D polytopes with D plus if we take the 77-dimensional skeleton of D polytopes with D plus 1,000 vertices, there's only bounded number of such creatures. A large number, but bounded. Okay, so I think this is a good point to finish this lecture. Thank you.
Thank you for the nice talk. There were some questions in between. Are there further questions? This was then.
Has this been classified? I mean, people worked on classifying these things for small parameters, at least in some social case?
Yeah, I think Perles had some written notes about that. So he started. You see, when you talk about general polytopes, you can form this pyramid operation. When you talk about simplicial polytopes, you cannot form this pyramid operation. So things can disappear and reappear. I think he worked out some classification for some very small parameters, but I don't think this was done beyond that. And there is some other twist to the story that I will tell you next time.
For simplicial polytopes, you have a bipyramid operation where you take a vertex and make it into 2.
But this increase the extra number of vertices by 1.
Well, we'll just keep it. You move one vertex and move to an
Right.
extra dimension and add 1 vertex. So
I know. But don't you add 2 more vertices
Pull
for?
one guy up and you add one guy on the other side.
Oh, you pull just one guy.
yeah, you pull one and
Yeah.
add another one.
But I'm not sure that this is so easy to describe what you do combinatorially, or yeah. No. Well, yeah. Okay. Yeah. Right. So you can you can do that. That's fine. Okay.
Further questions? We just thank you once more for the talk.